Hi everyone, this is Mike with a video trying to explain some important things that you should keep in mind about probability. I know folks typically have difficulty with probability, and this video is intended to help you manage some of that difficulty and I hope give you some useful advice as you work through this material. So I want to start off by giving some bad news. There is no quick fix or single formula or even set of formulas that are going to work in every situation. And that's important to keep in mind with probability. All probability problems are somehow different, even though they will usually have some things in common. So you want to treat them differently and think about each one carefully and separately. But pay attention to the things that they may have in common. So you do have to think carefully about each one separately from the previous ones, mainly because it's easy to confuse one type of problem from others that you've seen before. And even when different probability problems share common mathematical themes or threads, it's hard to see the commonalities because the contexts are going to change. And so you get probability problems about cards or coins or different surveys that they're selecting random people from. And even though those feel very different, oftentimes they will have common threads, and it can be difficult to distinguish how they're different and how they're the same. But there is good news. You don't have to be a super math genius in order to figure out these problems. Generally, all you need to know are some basic probability rules like the addition, multiplication rules, and rules about complements that you've already studied, and common sense can also take you pretty far with probability. It's not everything. That's why the rules and the mathematics are there, is to help you overcome some places where common sense can be misleading. But with some basic rules and common sense, you can get pretty far. Another piece of advice I want to give you here is that it's important to write the probability statement using language. A lot of times people will start to plug in numbers at the very beginning of their work on a particular problem, and that's usually a bad idea. When I do probability problems, as you'll see in a couple of examples, and I hope you'll see in some of the other video lectures, I'll write 4 to 6, sometimes a little more, sometimes a little bit less. I'll write several steps in linguistic terms, and then only near the end, in the last 1 or 2 steps, will I write any numbers down. And again, I hope you'll pay attention to the examples that you watch and that you see in the textbook. There aren't really any fancy tricks or special math behind the calculations, but you do have to think clearly and carefully about each situation that you encounter. So let's look at an example. 10% of us are left-handed. What's the probability of randomly selecting 3 people who are all left-handed? Well, notice that I start out here by using language only. So I'm doing the probability statement, the probability of choosing 3 left-handed people. And then I turn that into a much longer statement where I'm looking at the probability of choosing 1 left-handed person and then choosing a second left-handed person and then choosing a third left-handed person. Using the multiplication rule, because these are 3 separate outcomes, all of which are independent of one another. When I choose one person, the fact that previous people may have been left-handed will not have any effect on whether or not the person that I've chosen will be left-handed. Because these are independent, I can use the multiplication rule to say the probability of the first left-handed person can be multiplied by the probability of the second left-handed person, which can be multiplied by the probability of choosing a third left-handed person, all separate from one another. Each one of those probabilities is 0.10 because of the 10%, and when you multiply those all together, you get 10.10 to the third, which is 0.001. So you notice that I'm not using any numbers until almost the last step or two of the problem. And before I introduced any of those numbers, I broke the problem down using some of the basic probability rules that you've been studying. Here's another example. This is an example that folks tend to have difficulty with in the assignment, and so I'm choosing this one here. So this is an acceptance sampling kind of problem where you've got a sample of items randomly selected without replacement, and the entire batch is rejected if there is at least one defective unit. So a company, instead of testing all of their products, will choose a few of them, and if any of them are bad, then they will reject the entire batch of products. But if they're all good, then they will stick with them and ship them out to their various customers. So this particular company has just manufactured 4,000 CDs, and 140 of them, based on their previous work, they know are likely to be defective. So the question is, if we choose 6 of these CDs randomly and test them, what's the probability that the whole thing will be rejected? So notice again, I'm starting out using words here. The entire batch being rejected is the statement of the outcome that I want. I'm looking for that probability. And in order for the batch to be rejected, I'm going to write the probability that at least one unit is defective. Well, that phrase, at least one, is one in which there are other videos in this section that you can use to learn a little bit more about complements, but the phrase at least is a clue that you want to use complements here. And so the opposite of at least one is none. And so if I want the probability of at least one, I can subtract the probability of none from one, because these two together, the probability of none and the probability of at least one, that's all the possible outcomes. And so together those add up to 1. Okay, but then I write it again and I say, well, if none of them are defective, then that means that all of them are okay. And what does that mean? Well, all of them being okay means that the first one is okay, and then I choose a second one, and it is okay, and I choose a third one, and it is okay, and then I choose a fourth and a fifth, and followed by a sixth, and they're all okay. Again, using the multiplication rule, I can take those all separately, probability of the first times the probability of the second, and so on. But now I might be thinking, well, these things are not independent. The probability that the first one is okay, there are 140 defective CDs out of the 4,000, and so that leaves 3,860 CDs that are okay. So for my first choice, I have this many out of 4,000. And for my second choice, I have one fewer CD, and I have one fewer CD that's okay, so 3,859 out of 3,999, and then so on for the third and the fourth and the fifth and the sixth. So by the time I get to the 6th CD, I have fewer total CDs to choose from, and I also have fewer good CDs that I can pick. And if you do that multiplication, you get the value 0.19257. That's the probability that the entire batch gets rejected under these conditions. So notice again that I've done 3 or 4 or 5 steps even without writing any numbers in here. And I wait until the very end until I know how to split the probabilities up into much simpler events before I plug in the numbers. I want to say a little bit more about this example. First, pay attention to the fact that when you have a population of 4,000 CDs, choosing one CD out of that population doesn't change the population very much. So my first probability was 3,860 divided by 4,000. My second probability was 3,859 out of 3,999. And if you calculate those two fractions, you'll notice that they're very similar numbers. Not exactly the same, but very similar. What would happen if we treated these two outcomes as independent? In other words, what if the probability didn't change at all, even though technically these events are dependent? Well, that would basically mean that the probabilities don't change, and I can use the same fraction all the way throughout. Instead of changing it every time, I could use the same fraction over and over again, 6 times, because I'm choosing 6 CDs, which would be this fraction raised to the 6th power, which would be this decimal raised to the 6th power, and I get the very similar answer to the one I got before. Now it is different than the previous answer, but it's different by a very small amount, 0.0001099, which tells us that when we make the calculation easier doing this, it doesn't really affect the outcome all that much. So here's an important rule of thumb to keep in mind. If the sample size is less than 5% of the population size, you can treat the different outcomes as independent events. In other words, if the sample size is really small compared to the population, you don't have to make these changes to the fractions or the decimals in the probability calculations. You can sort of repeat them because the probabilities will not change. So here's a brief summary. When you're solving probability problems, remember that the numbers shouldn't come into play until the end of a process that includes several steps in which you're going to write English words as opposed to mathematical or numerical statements. Try to think through the original probability statement to see where you can apply basic probability rules like the addition rule or the multiplication rule. Pay attention to phrases like at least, where you may want to use the complement. So again, pay attention to those at least questions because they typically involve using a complement rule. Stay patient. Probability problems are challenging and take practice, but with assistance and persistence, you can improve the way you handle these problems and get more comfortable with them. Good luck.